Welcome to this lecture series in group theory. In this lecture, we won't be recalling anything from last time because we don't need it. These are the problems, and here we have a star mark problem, not because this is hard, but because we will be using this in today's lecture. So please take a note of this. Of course, I encourage you to solve all the problems, but these are especially important. Great. So the topic of today's lecture is Lagrange's theorem, which is most important theorem in group theory, especially in finite group theory. So let's start defining the relevant concepts. So what we have is, let's say we have a group G and H is a subgroup of it. And you fix little g in the group capital G. Then we define this notation to be equal to this set. And of course, this is a subset of the group G. All right. And if you solve the star mark problem, then you can see without much difficulty that the cardinality of GH is same as the cardinality of H, which is to say that there is a bijection between the set GH and the set H. And the bijection is nothing but just send x to gx, this map. So this is a bijection between H and GH. Great. So that's just a notation that we discussed, and there is a name to it. So a left coset of H in G, this whole phrase means a subset of G such that S is of a particular form. Which form? Such that S equals GH for some element G in capital G. So those subsets of capital G which are of this form are called left cosets of the subgroup H in the group G. So just a definition. And the set of all the left cosets of the subgroup H in the group G is denoted by this symbol, which is in notation. We have said something in words, but if you write that in notation, it just means the set. This set. The set of all the left cosets of H and G is denoted by this notation. And how do we read it? We read it as G mod H. This is how we read it. Right. And suppose G is finite, then the index of H in G is defined as this number. So the number of distinct left cosets of H in G is defined as the index of H in G. All right. So these are just some notations and terminologies. I hope these are clear. So let's move on. So suppose we have an abelian group. So if G is an abelian group, which recall just means that xy equals yx for all elements in G. So if G is abelian and H is a subgroup, then instead of writing, let me not write this, instead of writing GH, we may write G plus H. It's the same thing, just a different notation. And there's a good reason, as I'm sure you can detect. Basically, when you have an abelian group, the binary operation is typically denoted by plus. And that's the reason for this notation. It's convenient. All right, so now let's take an example. So again, fix some integer at least 2. Doesn't have to be that, but just for expository convenience, I'm taking it to be that way. And consider the particular subgroup of Z given by this equation. So of course, H is a subgroup of Z. So what are the cosets of H? So the cosets of H are, you fix any, take any integer A, then A plus H is a coset of H. So G is denoting Z. This is in fact by definition, all the cosets look this way. But what I want to say is that in fact, G mod H is nothing but 0 plus H, 1 plus H, up to n minus 1 plus H. So, well, there's not much going on here. I encourage you to think about this before you proceed. Why these are the only cosets? Because the reason is this. Suppose we had n equals 5. Then what I want to say is that 7 plus 5z, this is 5z is h, 7 is just some integer. This is nothing but 2 plus 5h. So 2 plus 5z, 2 plus h. Okay, and you can easily verify this. Everything here, anything here looks like 7 plus 5k, which is equal to 2 plus 5 into k plus 1. And hence, this is a member of the right side. Similarly, the right side you can think of, anything on the right side you can think of as a member of the left side. And that's it. So just stay on this for some time and you will get it. And we will say something more general than what we just discussed in the subsequent parts of this lecture. So basically the question is, when are two cosets equal? So formally, fix subgroup of some group G and fix two elements in the group G. Then the corresponding left cosets of H in G are equal if and only if this happens. And if you just look at this and the previous example, you will see why I'm writing G mod H equal to that. Okay, so let's give a proof of it. So first assume this, then y inverse x equals little h for some, this is very misaligned, I have to write that again, sorry. So then y inverse x is equal to little h for some little h in capital H. Okay, so therefore x equals yh, which implies xh equals that, let me put a bracket for clarity, which by definition is yhk, k varying in the subgroup H. Okay, but here's the thing. If we look at these things as k varies over H, what are all the things that we get? Now, if you look at the star mark problem, the elements that you get here are precisely the elements of H. Right? Anyway, H times k is clearly an element of H because H is a subgroup. So if you multiply two things in H, you will get something in H. But the point is, everything in H is of this form. And that's a trivial point, but still, one has to note that. So therefore, this is nothing but y, let me write k prime. And if still this is not clear, just look at the star mark problem and you'll get it. Okay. Fine. So what is this? This is yh. So we have proven one direction, that if this happens, then the above thing happens. So now for the other direction, assume xh equals yh. So then in particular we have x in yh. Why? Because x is here. H is a subgroup, it contains the identity. So x times identity is here, but x times identity is x. So we have that, which implies x equals yh for some h, which gives us y inverse x equals h, and that's it. So that basically is saying that this guy is in capital H. So a very simple proposition, but it's a very useful proposition. And we'll just make use of it without even mentioning any such result. We'll get used to it in no time. Okay, so this is a criterion for deciding when two left cosets are equal. And now we can prove Lagrange's theorem. So it says that two left cosets are either equal or they are disjoint. That's basically the theorem. All right. So suppose, what is that? So let x and y and b and g, these are arbitrary. And so we have corresponding left cosets, xh and yh. And suppose they are not disjoint. So suppose the left cosets are not disjoint. So what we would like to show is that they are indeed equal, which would prove the proposition. Well, the proposition says a little bit more, but right now let me just show that if two cosets are not disjoint, then they are equal, and we will then prove the proposition. All right. So suppose they are not disjoint, then we will show that. these are equal, but that's actually very, very clear. So suppose, so pick some common element. So if they are not disjoint, then there is some common element in them. So what we have is thus G equals xh1 and G is also equal to yh2 for some h1 and h2 in the subgroup H. All right. So here is what we will do. So we have G equals xh1, and from the second equation we will see G inverse equals h2 inverse y inverse. Okay. And now we multiply these equations. So G inverse equals, or rather the other way. So G inverse G equals h2 inverse y inverse x h1. Right? So what we did was we just multiplied this with that. So on the left side we get G inverse G, on the right side we get this multiplied by that, which is what we've written. So this is implying that identity is h2 inverse y inverse x h1, which implies h2 h1 inverse equals y inverse x. Okay, I think I need a new page. All right, so what we have shown is that y inverse x is h2 inverse h1. But the point is that this is a member of H. It's a product of two things in H. So it is a member of H since H is a subgroup, which gives us, which by the previous proposition tells us that the corresponding left cosets are equal. Okay. So far what we have done is shown that if two cosets are not disjoint, then they must be equal. So to show that the left cosets of H in G actually partition the group, all we need to now show is that the union of all the left cosets is the entire group. Let me draw a picture. So we have this group, and what we have shown is that two distinct left cosets have to be disjoint, because as soon as they share one element in common, they become equal. So any two distinct cosets are disjoint. So these rectangular things I'm drawing are supposed to depict cosets. So if we can show that every element of the group lies in at least one left coset, then we have shown that the left cosets partition the group. But that is very easy, because if G is some arbitrary element of the group, then G lies in this particular left coset. So therefore the cosets together cover the whole group, and by the property that if any two distinct cosets intersect, then they are not distinct, they are equal in fact. So two distinct cosets do not intersect, and this proves the proposition that the left cosets of H and G partition G, and this is Lagrange's theorem. So this has nothing to do so far with finite groups or anything. This is a theorem about any group. But a certain consequence in finite groups is of utmost importance, is that suppose you have a finite group G and H is a subgroup of it, then the cardinality of the subgroup divides the cardinality of the group. And I want to make a comment that cardinality of a group is also called the order of a group. It's just a terminology. Okay. So how do we show this? We already have that. The left cosets partition G. Left cosets of H, left cosets of H partition G. And each left coset of H is of size the same as the size of H. So basically you have this kind of partition of the group. This has size cardinality H, this has size cardinality H, this has size cardinality H, and so on. So this must mean that cardinality H times some integer, whatever that integer might be, let's say k, this is equal to the cardinality of the group, which implies that cardinality of H divides the cardinality of G. So that's a very interesting result. It's not at all obvious immediately from the definitions. And many times, this is what is referred to as Lagrange's theorem. So both these propositions will be referred to as Lagrange's theorem, this one and that one. But really, the previous one is the heart of the matter. Okay, let me just make a comment about right cosets and end this lecture. So fix a group and a subgroup of it, and take some arbitrary element in the group. Then this notation is supposed to mean this particular subset of the group. And exactly the same discussion goes for this notion of right cosets. You can prove Lagrange's theorem very similarly, nothing very interesting. I also want to say that it is not necessary that a left coset is equal to some right coset. It may just not be true. So you may have a left coset, but there may be no right coset which is equal to that left coset. That can happen. Anyway, so this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.